not expect that magnetic fields would enhance growth rather than suppressing it, for instance. So that's that. All right. So I'm going to turn to a related topic, which is to say, instead of like looking at one of these clouds, let's zoom in on where all the action happens. Instead of looking at this scale, right? Let's look at this scale. This is where the cold gas is being mixed into the hot gas, and depending on essentially the ratio of a mixing time to a cooling time, there's mass flow either from the hot gas to the cold gas or vice versa. And then, as we've also argued, this also implies momentum transfer, right? Because there's momentum conservation. And so if the hot gas cools on to the cold gas, then that changes the momentum of the cool cloud. So how can we understand this process? What's the rate at which it's occurring? And, what scale do you have to resolve to converge in this process? This looks like a very scary process in the sense that as you run at higher and higher resolution, there's more and more small scales, right? This is true of any, like if you run any Kelvin-Helmholtz simulation, you'll see more and more structure. So, and in fact, Drummond fielding showed that this surface is in fact scale-free. It's a fractal. And if you zoom in more and more, it's you just get more and more structure. It's like the coastline of, was it Dover or somewhere? You just look at it at higher resolution, and it becomes longer and longer. So the crazy thing is that, so you might just give up at that point. You just say, I can't have a simulation that has that resolution. And these things are ubiquitous, right? We think that they're cold streams in high redshift halos, redshift 2 and 3, which plunge in and feed the central galaxy, right? We know that there are high velocity clouds in the Milky Way that are falling in and undergoing mixing, right? And we see jets, for instance. Everywhere you look, there's shear and there's radiating. And how do these things interact? And what's the resultant exchange of mass, momentum, and energy? So the shocking thing is that although when you look at these, they have so much structure, and there seems to be more and more surface area as you go to higher and higher resolution, that the actual emission you see, the total cooling rates, and the mass transfer rate from one phase to another are numerically converged at very low resolution. You can run a really embarrassingly terrible simulation like this, and you can run a tiny bit more respectable simulation like this. These will have the same integrated cooling rates, when it really looks like it should not, right? And so why is that? And this is what I mentioned. So this is a paper by Drummond Fielding where he showed that that cooling surface is fractal. And if you look at how the area scales with resolution, there's a power law scaling. And as you go to higher and higher resolution, there's more and more surface area, which should imply there's more and more cooling, right? So, so why are you converged? That seems like great news for completely inexplicable reasons. So as I said, mass growth is converged as you go to higher resolution, and area growth is not, consistent with what Drummond was pointing out. Right. So, I think the answer lies in what what people have been doing in turbulent combustion, right? So these people are a lot better funded. They have even fancier computers because it's of great interest to try and have good fuel economy. right? You want your cars and your jet engines not to waste anything. You want to maximize that burning surface area, right? And so this is one of those cases where actually an early paper is readable. Well, I didn't read it. I have a collaborator who's German, Max Ronke, which actually is very illuminating. And so I think if you want to boil down to the basic idea, it's just something that's quite familiar to you from turbulence, right? If you're trying to mix cream into your coffee, right? Then how is it that you can mix it, right? If you calculate a molecular diffusion time, that time scale is forever, right? You should not be able to mix it. And so what happens here is that as you mix it, the surface area increases more and more and more until you have such a large surface area that the molecular diffusion time becomes actually short enough. And then you actually do mix at that scale. But the actual time scale of mixing is determined by the rate at which you're stirring it, right? So it's determined by the eddy turnover time at the outer scale. And you don't have to resolve the molecular diffusion to know how long it will just take a couple stirs of your spoon. It doesn't really matter. So it's the same sort of argument, like, when you stir something, you don't really care about the actual viscosity as long as you cascade down. Eventually you'll turn all that stirring motion into heat. And so it's a sort of similar thing. If you mix two phases, eventually, right, one will cool, the hot phase will cool onto the other, and it doesn't matter. Now, I should add that, it's interesting to ask what happens, when you add microphysical processes, really like conduction and diffusion, and you change their laws. And there might be regimes where it's somewhat sensitive to it, but it's not order unity sensitive. And there's many, many different regimes in turbulent conduction where they try to list out the different behaviors. But I think, at the grossest level, this sort of makes sense. So you can make predictions about how things change based on a dimensionless parameter, essentially the ratio of an eddy turnover time to a cooling time. And, when turbulence dominates, meaning that the turbulent time scale is short compared to the cooling time, it looks more single phase. And if the cooling is strong compared to mixing, then you get something that looks more multi-phase. And you can derive analytically scalings of surface brightness in these different regimes. And the simulations agree well with the analytic scalings. So, so that's nice. And so you might ask, well, can I predict a net cooling rate, right? If I'm stirring something, right, what's the net cooling rate? It's something to do with mixing. It's something to do with cooling. But then in the end, what's the effective cooling rate? And it turns out that it's geometric mean of the mixing time and the cooling time. And this is something that we actually know from other processes, right? Like in your probably first year, you take some Rybicki enlightenment class, and then you ask, all right, if I have radiative transfer in a medium where I have both absorption and scattering, then what's the rate at which my photons are destroyed? And the stuff are random walk, and then at some point they hit an absorbing particle like dust and they're absorbed. And if I'm more scattering, I'm going to absorb more, right? Because my path length through the medium is longer. And you have this answer that is the geometric mean of those two things. And similarly, when you have thermal conduction, which is elastic scattering of electrons, and cooling, which is inelastic absorption of electron energy, there's a characteristic length scale, the field length, which actually is the geometric mean of the cooling length and the elastic Coulomb mean-free path. So it's a nice kind of analogy from these processes to essentially, I guess, essentially turbulent elastic scattering and inelastic scattering. All right, I think I'm going to skip this. Maybe this is too much in the weeds. So then what does it look like, right? Can you get an idea of what sort of things are we looking at? You know, is it like San Francisco? Is it like a fog? Or is it like, I wouldn't say Los Angeles, Great Britain, where it's more cloudy, right? So an example of this is something like, you know, situations where you see fluorescent emission, right? You have stuff where you know the gas is very overdense because you see it in emission, and you need a certain density to produce a certain surface brightness. And if it's 1,000 times overdense, the most volume filling fraction you can get is 10 to the minus 3, right? And if the coal gas is only is a fraction by mass, then it's going to be smaller. So you have something that, you know, by volume is tiny, and yet by area covers a lot of, you know, most of the halo. So how can you arrange this? Maybe you can just arrange a shell that would do it, but otherwise, it seems very strange. Another thing that you see is that you can have quite superthermal line widths. It's much bigger than the internal velocity dispersion of the coal gas. So, you know, as I hinted, well, suppose it's like San Francisco, right? Then the water is a tiny fraction by volume. The water vapor is a tiny fraction by volume, and yet, you know, it can have a very large area covering fraction. And the secret to that is that the water droplets are tiny, right? So you can spread a lot of them over a large surface area. Surface area to volume just scales like 1 over the size. So if the size is tiny, then you can get a lot of area. So Mike McCord was responsible for this idea that, you know, if you had stuff which lost pressure balance with its surroundings by strong cooling, then you could break up into very small drops, right? So this would be something he called shattering. There's other ways of getting, you know, breaking things up into small pieces. You know, Kelvin-Helmholtz instability shear is another example. But, you know, this seems like, yes, there should be lots of small scale structure, right? And that can explain why you can cover a huge area with only a small amount of stuff. But then at the same time, you know, I told you earlier this whole story that you needed a minimum cloud size to survive in the first place, right? And this cloud size to survive is much bigger by an order of magnitude than the scale at which things shatter down to. So that seems strange, right? So is there a characteristic scale at all? And so it seems like, no, there's no real scale. And so this is a simulation where you run a turbulent box with radiative cooling and this coal gas. And then you see, you know, you see a lot of structure forming. If you look at the mass function of this stuff, then it's a scale-free, it's more or less a scale-free power law. So that means that you have mass which is broadly distributed across a range of scales. So you get the large clouds that are required for survival, but those also fragment into small clouds which do not survive, but they dominate the area. So you can cover a lot of area even though you have a small volume filling fraction. And so this thing, right, this is a dm of m to the minus 2, and this is known as Zipf's law. And it applies to an astonishing range of systems. I became quasi-obsessed with this. It appears in a lot of things, it appears if you try to measure the bubbles in breaking waves, size distributions of dust and asteroids, aerosols is another thing that people spend a lot of money investigating. But it also appears in income distributions. It appears in the population of city sizes. There's a ton of literature in economics on this. I have many nutty ideas. I heard there's wine and cheese after this. That's the appropriate forum to talk about this. I could go on for before it was for whatever, for employment. This is love. Okay. I once gave a long seminar about this where in the first slide I said 99% of this talk is wrong. And then someone came up to me and said, the first slide was the only correct slide. I think it's a fun thing to think about. And in all seriousness, I think this, if we can pin down, something like this, where this comes from, it's something like, the stellar IMF also has similar behavior, right? And people spend a lot of time trying to think that. And this is a sort of analog of that, except that instead of being gravitationally confined, here your mass lumps are pressure confined. And I think there's a lot of interesting physics there, to be less facetious. So let's see. I'm just going to sort of present a smorgasbord of things I think are interesting. I don't know how interesting they are to you. So one of them is just this multi-scale problem that I mentioned, that there's so many scales to cover. So what's the future direction of this, right? How are we actually going to resolve this problem of galactic atmospheres, in a way that, say, climate scientists are trying to do for the Earth's atmosphere? So one approach, right, which Cameron is involved with, is to try and do two fluid simulations where you treat the cold stuff and the hot stuff separately, and they exchange mass, momentum, and energy with one another and try to parameterize this, right? And it's a perfectly sensible approach. That's how we do radiative transfer, right? That's how we deal with cosmic rays. We essentially treat them both as different fluids. So this program is in early days, right? There's many groups trying to pursue this. It could be promising. As far as I can tell, nobody has really been able to, say, take a very high resolution simulation and reproduce the same results with a low resolution one with this kind of recipe. But, I think there'll be a lot of activity on this front. And the other thing is that, there's this whole GPU revolution, right? There's exascale computing is coming. And it's possible, right? If you study the scales carefully in small scale simulations to say, you guys just need to resolve, couple parsecs and you're good. And, we could be getting there. And so that's just another direction that, computers may make up the difference. Years ago, there was a facetious paper by University of Arizona graduate students where they said that it's always better to not work on your project because Moore's law will improve computing, that you'll actually make more progress by just resting. So this might be the case too. So I think, one thing that would be dear to my heart would be to try and understand, this cloud IMF, for instance, the distribution of cloud sizes. And there's many physical processes involved with this, growth, fragmentation, and coagulation. This last thing is kind of neat because this is something where you just put a bunch of clouds, right, in a hot medium. You just let them sit there, you perturb them a little, and eventually they'll coagulate. And this is all done by mixing, and it's drawing in hot gas that brings them closer together by removing the interstitial hot gas, and then they merge. And this turns out in the nutty thing that I did not talk about to be crucial to producing the power law. Yeah, but we'll probably save them for afterwards. But so this stuff turns out to be also the leading source of uncertainty in climate predictions because of the vast range of scales that you need to resolve, right? You also need to resolve the physics at cloud interfaces, which is meter scale or smaller and tiny. And so they also use subgrid models. And so these guys have been in this business a lot longer. They have very clever machine learning techniques and all that. So this is probably a region that we could stand to steal some ideas. And then, another thing that you really want to, you care about is just, this realization that small scale physics can feed back up to larger scale physics. A prime example of that is transport coefficients, right? You have electrons random walking, that affects thermal conduction. You have ions random walking, that affects your viscosity. And then you have non-thermal stuff, random walking, like cosmic rays. And that's a separate fluid that many people here work on that can transfer momentum and energy to gas. And it's thought these days it's thought to be potentially very important in feedback. So how can you probe these very small scales, right? I think this is a paper that came out very recently that I thought was absolutely on the right track. You basically want to utilize local observations, right? So, density fluctuations can be probed on very small scales by radio wave scattering, right? You can even do it in sort of distant galaxy halos from FRB observations, right? And so if you have a mist, that could scatter radio waves quite a bit. If you have turbulence, and I've been trying to take radio astronomy lessons from Stella. She's looking displeased. But I just put this up to show that this Fresnel scale, which is a diffractive scale, is AU, right? We're talking about AU scales, in something that's cosmological distances away, and the actual stuff that's doing the scattering is considerably smaller with that. And there's still a chance of probing it. And if I'm right, if you're also talking about scattering down to dissipation scales, which are tiny, thousands of kilometers. So anyway, I should skip over before she starts. Okay, I think maybe I should, and cosmic rays are another thing that explore all these small scale fluctuations. There are interesting issues about whether such things diffuse like normal diffusion. There could be anomalous diffusion, which people see in simulations where they have turbulent magnetic fields and they trace particles through them. They see super diffusion, they see subdiffusion. Here, Naising Liang, she looked at this with a Monte Carlo code. And you can see regular diffusion, the step sizes are small, right? They're drawn from a Gaussian distribution. But if you have super diffusion, for instance, there's a power law tail, which means that most of your transport is dominated by very large jumps. So this could potentially change how cosmic rays propagate. But I think one thing that we realized is that in a finite system, they escape. And eventually, this reverts to regular diffusion. I probably should, yeah. I think, so just, we don't really understand how cosmic ray transport works. It's one of those things where we're doing radiative transfer without knowing the correct opacity. So there's a lot of freedom in how things could develop. And, I think this is just an example of the uncertainties that we face. So, okay, maybe if this talk has been a very sort of theory, spherical cow heavy kind of thing, So you're like, show me a little bit of the real world, right? How can you test this stuff? Which I think is a very fair objection. We're not going to be able to see clouds in any of the resolution that I talked about. Even in our own Milky Way, we see high velocity clouds, but it's still not so easy to say, well, this is a test. The theory is correct or not. But there is a lab which is very close to us where you could potentially test a lot of these multi-phase ideas. It's in the same temperature range. Here's 10 to the 6 K gas. Here's 10 to the 4 K gas. And this is the intermediate temperature gas, right? And this is the regime where Eugene Parker first wrote about when he wrote his seminal, his paper in the 1950s about thermal instability. And George Field, in his 1965 paper, this was one of the prime applications, right? This is the solar corona, and we see tons of stuff there. We see coronal rain, stuff that's condensing via thermal instability and falling to the surface of the sun. And we see it in real time because the time scales is minutes to days. And you can see resolved structure on very small scales, and the magnetic field structure too. Now, there's an important difference is that the solar corona is much more strongly magnetized than what we think the CGM is. But that's something that you can account for in your simulations. And I think a lot of the physics is very similar. And there's probably not as much interaction between these communities as there should be. I mean, when was the last time you heard a heliospheric talk? I don't know why it is. Like, there's just this, there's solar physicists and then there's the rest of us. And there's a lot to learn from those guys. And I think conversely, like, we worry about things that, they may not care about. These things are falling, right? There should be mixing. There should be all the processes we talk about. There's no good evidence for thermal conduction anywhere in the ISM. So I shared an office with Chris McKee at a KITP program. So I got it from the horse's mouth. He's like, no. This is the man who worked on this, you wrote seminal papers on this. So, but here, I mean, you have all of these highly spatially resolved simulations. If there's a conduction front with intermediate temperature gas, you should see it. And I asked the solar guys, and they were like, yeah, we should go look for that. I don't think they were worried about constraining thermal conduction. So here's an example of, just to wrap up, here's an example of a calculation that we did that had no solar physics motivation, right? We were just trying to do this thing about magnetized shattering. So basically, I talked about this idea that if you had strong cooling, where the cooling time is much shorter than the sun crossing time, you break up into lots of tiny pieces, right? And this was Mike McCourt's idea. And then this is what happens, right? You break up into tiny pieces. So this was not at all motivated by solar physics. When you give talks, people are like, well, what about magnetic fields, right? It's like saying, what about dust? So finally, got around to it. And yeah, indeed, the answer is completely different. So, all the naysayers were correct. They're like, and okay, is that. So what is going on? I'll give you a short version. There's stuff involving the thin shell instability and all of that. But basically, in hydrodynamics, you cool, you lose pressure, and then you compress, and then you rebound, and then you fragment into lots of tiny pieces. You can't do this in MHD because fundamentally, magnetic pressure is anisotropic, right? You can, along field lines, you don't see, so the field lines are this way. Along field lines, there are no MHD forces, and you can free stream. You can't compress field lines too close together because magnetic pressure will take over, and it doesn't like that. So what happens is that when you have a large thermal pressure difference, you feel thermal pressure gradients along the field lines, but across the field lines, you're sustained by magnetic pressure. So then you get the streaming along field lines. And it took us a long time to convince ourselves, but we think we understand this very well. And the reason for the counter motions is there's fragmentation by the thin shell instability, and we've looked at this in a lot of detail and understand it. And you can even look at it in just if you have a simulation box with regular thermal instability, you get this crazy behavior, right? And we were like, come on, this has got to be nuts, right? When is this ever going to happen? We've never seen anybody talk about stuff like this, so we would just assume that we were doing something crazy. But check this out. This is not a simulation. These are observations, okay, by some NASA thing that I will praise highly in some next grant proposal. And if you look at this, that's counter-streaming gas motions right there. I'm told they're better movies, but I couldn't find it in time for this talk. But yeah, and there's all kinds of other interesting effects. Like there's characteristic scales. They see this in this thing. They don't understand. I talked about accretion drag and terminal velocities. The terminal velocities, which are, there's acceleration down to the surface of the sun. That's small. It's much smaller than the gravitational acceleration. So there's some drag force that's very strong that is still not very well understood. The streaming velocities they see are consistent with what we have in those MHD simulations. So I'm excited about this. I think trying to go to somewhere where you can see that you have great temporal and spatial resolutions is really what we need. Because I could run all the cloud simulations I like. I don't think it will convince anyone here, right? I think we're dealing with a real universe. We need to compare to real observations. And just saying that I can get coal gas outflowing, just like what you see, that's not good enough. It's not like this is actually mechanistic, right? You can see emission lines from a huge range of temperatures, all from 10 to the 4 all the way up to 10 to the 6. And you can tell if that's consistent with the cooling rates that we predict. We predict from mixing, the temperature PDF, so forth. So I'll just leave it at that. Mm-hmm. 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 Right. Right.
At fairly high temperature.
Mm-hmm.
Physics, active gas, but this is a lot of microphysics and non-equilibrium physics.
Right.
Association by UV, the UV is anisotropic. It seems like a very foreign thought to me.
Right. So this is, I'm really talking about the circumgalactic medium and less the ISM. So this is motivated by observations where you're really probing, the atomic gas, essentially. Yeah. Yeah. So, I think I was once babbling about the CGM, and then, a prominent astronomer said, the CGM is just the ISM with crappy observations. To some extent it's true. It's the same physics. But I think the molecular component does come in the sense that you do see dusty gas at quite large radii. And if you think about how the coal gas, if you want to say, I'm making this, yeah, but it's just how does it survive? If you try to make the cool gas via thermal instability, that dust is not going to live very long in the hot gas, right? You get destroyed by sputtering. So, you have to somehow take it from the central galaxy and move it out. And that's the interesting challenge. Yeah. Cameron?
So I thought digression where you're showing when you have magnetic field versus the non-magnetic field case for the thermal instability. But it wasn't clear to me when you included the conduction how you got that anti-parallel behavior that was shown in the
Okay, let me.
Not this one, the next one. When you include the conduction, why it leads to the
Well, both of them show anti-parallel behavior. It's just you know, the length scales are, well, why can't I play both of them at the same time? So here you have counter streaming too, right? And here you have counter streaming as well. The main difference is that with conduction, the parallel length is larger. And you might think, well, it should just be the field length. It's not. It doesn't scale like that. I mean, it increases in the same direction, but it's not. And apparently in the solar corona, you know, they don't understand the sizes of the coronal rain filaments they see. So we've started to try to collaborate to look at that. Yeah, it's an interesting problem. Yeah. These are just MHD simulations. So the ingredients in all these simulations are very basic. You know, it's just MHD plus radiative cooling. It's sort of kind of amazing that you can get such rich behavior. Like this is like vanilla simple, really. And everything that we've found, it's not like we were thinking, oh, well, we intuited it and then we predict that we will see this, and by the power of our intellect, yes, we found it. It's more like this emerged and then you're like, what the heck? Yeah.
The talks in case we have further questions. I think it's time to move on to the section where you said ask me over an alcoholic beverage about all the ideas. So on that note, can we please move back towards wine and cheese? And I'm going to ask to remind everyone that we're going to so please make your way.
Yeah, it was fun.